Okay, so welcome everybody to the big seminar series in this new academic year. We are very happy that our own deep fellow Christian has agreed to speak on the opening day, and he'll talk about cluster formation in
Yeah.
evolutionary time.
Thank you. Yeah. Well, I'm here on explicit invitation by Tuan, so he has to be focused, and we will, ask him questions later if he understood everything. Great, he's closing down his laptop. So yeah, I've given versions of this talk to some people of you before. Not everybody has seen it, but I think it's also slightly more extended. Of course, it's a deep talk, so I have at least an hour, or so I can just do this more slowly. Yeah. And of course, there are also some more biological slides, and then probably Andre has opinions, and then we can spend 10 minutes discussing. That's right, yeah. And now the clicking stopped.
I guess the drawback of not using the screen is that we don't have its microphone. Maybe it's good if you stand behind your laptop.
Yeah. So can people online hear me? Is that, yeah. Yeah. If there are no people, yeah, people say yes. Great. Okay. Well, what is some sort of the idea behind this whole idea? This is some sort of called the paradox of the plankton. The idea is you just go somewhere to the ocean where a lot of plankton species live. You just, get your scoop of ocean water. You start counting all the different species that live in this part of the ocean, and you will find that there are a lot of different plankton species living at the same spot in the ocean. And this works in general if you also just go somewhere in the forest, start digging some soil and start counting all the different insect species, worm species, so on. There is just an enormous biodiversity on Earth. And of course, if you just think about classic Darwinian evolution, like the most fit species always outcompetes all the other species, then the idea is there shouldn't be so much diversity. We should only see one plankton species, or maybe a handful of plankton species, the most fit species. And mathematically, this is known as the competitive exclusion principle. I mean, if you just have different species, they are interacting, they are competing for food, you write down your set of ODEs, and you compute the limits, stable points, you will know that there is just a small set of species that can coexist at the same time. Now, of course, as a sort of the idea is, this is a picture about bacteria. You have here 4 bacteria species competing for 3 resources, then the math will tell you that in the end, only 3 species should coexist. But if you would do this in an experiment, you will see that many more than 3 species coexist at the same time. Now, of course, this debate has been going on since probably somewhere since the 60s, since Hutchison formulated this paradox. And actually, I think most biologists will agree that there is no really such thing as a paradox. It's just like, so it's a sort of a question that we need to think about. If I just write down ODEs, I will get not that much of a complexity, but we see complexity in nature. So there are lots and lots of ways how we can think about complexity. But sort of for me, the paradox of the plankton is more telling us that we have to think about complexity in ecosystems and think how these things evolve. It's not some sort of a given fact that plankton populations should be very complex. But of course, in the past decades, there have been many different ideas. Of course, there have people who probably claim the reverse, like the real paradox is that there are not enough species. Of course, you can claim spatial heterogeneity. It's like, yeah, well, you show this competitive exclusion principle using ODEs, but we can't model the real world by ODEs. I mean, we have actually space that you can move around, and this will get rid of a lot of the mathematical issues. Competition, that's not the only point that limits a population growth. And of course, the point is that, like in this simulation here, we went to t to infinity and studied what happens. But of course, ecosystems are never in this t to infinity case. Ecosystems are never stationary. There's a lot of variation going on. Of course, you have all the seasonal variations. We have weather, stochasticity from other sources. The dynamics can be kind of chaotic or oscillatory. And of course, there's this whole problem of time scales. I mean, so we assume in this figure that all the parameters in this system are fixed, and then we compute the limit of t to infinity and see what happens. But of course, if some of the parameters would change halfway during the simulation, then of course the outcome would be different. So the question is the time scale on which this dynamics happens, that would exclude this species from the system, is this a very short time scale compared to the time scale on which all kind of other things change in the system? I mean, for example, we have here in Europe, we have this switching back and forth between ice ages and inter-ice ages. I mean, this happens over periods of tens of thousands of years. But if some sort of the time that the system needs to equilibrate also happens on this time scale, I mean, then we're never in this t to infinity case. So as you can see, and also the last one I want to discuss is the so-called trait-based community ecology. Some sort of the idea here, and we will discuss this a lot more today. But the idea here is that a lot of species are actually very similar in the sense that you think of evolution of the most fit species as a species that is better in doing things than another species. But in many cases, species have a certain budget, like they have 24 hours in a day, they have a certain amount of energy, and they have to spend this energy and time on, sleeping, reproducing, getting food, taking care, whatever species have to do to survive. And if you want to get better at one part, you have to get worse at something else. So the idea is a lot of species are constrained by budgets. And if you include budgets into your mathematics, then suddenly the whole problem of competitive exclusion also disappears. So these are all things, and if you're a biologist, you probably have your own opinions about the slides, your favorite reason why the paradox does not hold or might hold, or what is interesting or not. But I'm a mathematician, so I will from now on focus more on the mathematics.
Can I ask you about the last argument that you made there?
Yes.
Community ecology, because wouldn't that imply that somehow some neutrality among species, that you are on a kind of, if you say sum of all traits is constant, it sounds to be like that you are in some whatever hyperdimensional space of traits, and you are on a neutral, on a manifold where everything is neutral.
You're on a lower dimensional manifold. It's not necessarily neutral. You can be. I mean,
otherwise you can't get every species to coexist. I mean, like.
No. We'll see this in the next slides. The dynamics isn't neutral, but it is indeed constrained to a lower dimensional plane. And on this lower dimensional plane, as many species can coexist under certain mathematical conditions. So it's slightly different than Hubble, as far as I understand. It's also there's no stochasticity involved. I mean, in Hubble there is this idea of stochasticity, but this is all deterministic.
I have another question.
Yeah.
So you can think of this selection as taking place at the species level, from which the paradox comes.
Yeah.
I've also heard people make the argument that actually the selection happens on the genetic level.
Sure. Yeah.
Do you see this? Is there this paradox also genetically, that there's an incredible range of genomes? Or actually these different species that you find, are they genetically very similar?
I'm not sure how this is the case for specific plankton species or not, but in general, healthy populations of species have a very high genetic diversity.
Right.
And of course, I mean, and this also helps with reacting to changing environments. I mean, if you have a lot of the genetic diversity and suddenly the climate change, by increase of 1 degree, then this will force some dynamics on the gene pool. And this is something that always happens. So the more diverse the gene pool is, the better it can react. And these are things that can happen also on very short time scales. This can just happen over generations, and a certain genetic variation that is already there in the population suddenly becomes very popular if this is something that happens. Yeah. And of course, for all my mathematics, it is really, from the moment we start doing mathematics, I always have my one species. But you can also really think about one species as just one genetic variation within one species instead of one species within a community. Of course, the mathematics is actually not that different. Yeah,
I also have a question at very low level. So does it mean that this paradox impose like the exclusion principle impose that one species, one resources, like one
Yeah, so if you
species,
have n resources, you will have at most n species living together.
But then what happens if one species can like use several resources? Then
It could also be lower than, I mean, if you have 5 resources, it could be that there is one species that outcompetes all the other species, and you get just one species. But the maximum that you could find is given by the amount of resources. It can also be lower, but the maximum is given by the number of species. Yeah. Was the question?
No, somebody low in.
Okay. Of course, so what we want to do in this project is some sort of think about like how can we some sort of construct complex ecosystems from the ground up, just in silico, just by doing computer simulations. And of course, some sort of rephrase, what is the minimum number of constraints that we need to enforce on our system to observe some interesting or complex ecosystem dynamics? I mean, if I write down a lot, if I put a whole lot of information into my computer simulation, I will get something interesting out because I put a lot of interesting stuff in. But that's not what we want. We want to see how little can we do and still find interesting results. So the general approach will be something like this. We just write down a whole vector of organisms. So we have all these different species xi. They evolve around some ODE. They're indexed by a whole set of parameters theta. And the idea is, okay, at some point in time, we choose one of the species in our system, and then we introduce a new species to our ecosystem that is just a small perturbation of an already existing species. And so in that sense, we mimic evolution. And of course, this gets a small, for example, we say, we have this, let's say we choose species number 5, then we introduce a new species. We get 5% of the biomass of species number 5 and has parameters that are a small perturbation of the parameters of species 5. And then, of course, we'll just keep on repeating step 2, and we remove species I when it falls below a certain threshold, and then we say the species has gone extinct. And we'll go into more details later about what we're going to do, but this is the general approach that we take. Yeah.
This theta is a smart parameter?
No. Theta is just a parameter, that's even a matrix, I think, because we have for every species, we have a whole range of parameters. Yeah.
It should be a vector, I mean, it should be a matrix, okay.
It's a matrix,
This
yeah.
is a scalar. So it's the-
Oh, yeah, it probably should have made it bold or something like that. Oh, yeah. Yeah.
One particular species.
Yeah, that could also be an option, yeah. Yeah.
But then it can still be.
Yeah, but could be affected by, yeah.
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 For every species, you have a lot of parameters.
Yeah.
So, but it's not a fixed dimension, not fixed.
No, the dimension of these matrices change all the time because I'm adding species and I'm removing species.
And this F is that's sort of universal, it's independent of I.
It could, yeah, it could be also dependent on I, but mostly for simplicity we take the same thing. But yeah.
do you have some timescale separation here for the acting frequency? Like how frequent you add a new species?
Yeah, that will be. So as I said, we will later focus more on the specific steps of what we're doing, but there will be a timescale separation. Yeah. Yeah.
Species I depends on, well, how many there are species.
Yeah.
On some function, which is not dependent on I. Yeah, which is the same for every.
So it's implicitly dependent on.
Yeah, so maybe the slide is now more confusing than helping. It's just like, okay, just think about this as there is an ODE. Yeah. There is a system of, and we will look at the next slide, a specific example. So at this point, just there is a system of ODEs that we're evolving. Yeah.
Well, but it does say something more specific, right? It doesn't just say there's an ODE, it does say there's a similar functional form for all species. What changes are the parameters
Yeah,
in this functional
indeed. Yeah. 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 So of course, one of the classic examples is the Lotka-Volterra equations. I mean, you've seen these kind of things before. We have this logistic growth term here for the prey species. We have this predation term here, and you get the predator species, and then you get these nice oscillations. Yeah, this is a sorry. Oh, sorry, you don't get. You have to send k to infinity to get these oscillations. Yeah. You're sharp after a whole summer, yeah. Yeah.
All this stuff.
Yeah. Yeah. But yeah, I've given this presentation multiple times before, and the other people, it's good. Yeah, no, it's good. And of course, other things that you can think about are general like resource consumer models. So where we have a whole bunch of resources given by R and indexed by J, and we have our species and indexed by I. And then of course, for all the resources, we get that they are, of course, consumed by the consumers by definition, and they have a certain replenishing rate. And of course, for all the species, we get that they're able to consume they have a certain ability to consume a certain resource J. And of course, how much they can consume depends on how much there is. Then, of course, each species also has a certain mortality rate.
So, don't you just with Lotka-Volterra, do you not
Yeah.
already sort of see that you don't go to this place where the fittest species survives? Is Lotka-Volterra not already enough to show this intuition doesn't hold?
No, I think
Specify Lotka-Volterra. Predator prey or competitive competition?
What we just saw.
Oh, that was predator.
Predator
Yeah.
prey.
and so of course in
You already
predator.
see oscillation.
Yeah.
That's already not this plot showed at the very beginning where just one species survives and the rest all.
No, that was purely resource consumer. That's purely this case.
Okay.
Yeah.
Okay, sorry.
But the thing is that probably you can start with this picture, and you can find the parameters that you have k to infinity, you fill in these parameters and so on. And then of course the question is, okay, now I start building more complex system, like I'm adding a second, I'm not just have a lynx, but I'm also adding a fox, and I'm not just have a bunny, but I'm also adding whatever else to eat. A ferret is also a predator, and like another prey species, two different types of bunnies. Yeah. And if you then, want to find such a system that has these oscillations, and you're looking for parameters that actually give you this, that will be very tricky. If you just start building an ODE, you take a 4-component ODE, starting filling some parameters, press enter in MATLAB and see whatever happens, or Python, probably Python in your case. You probably won't find any interesting oscillation. You have to, search very hard to find an oscillation. And of course, the bigger your system gets, the harder it will be to, by accident, find something interesting.
Okay.
And of course, you can deliberately construct your parameters in such a way that you will find interesting patterns. But if you just randomly start adding parameters and press enter, you won't find interesting dynamics, or it will be very hard to find interesting dynamics. Okay, so this is one of the resource consumer model, and I think this is the one we will.
Much more to say about it.
Yeah, of course. I mean, but of course, let's say these Lotka-Volterra systems. I mean, this has been formulated in the 20s, I think, somewhere around that, and this is so we're now a century old. So the amount of mathematics that exists, so both the results from just the theoretical literature, as mathematicians who went to town with these equations, is just enormous. So I am not the qualified person to speak about this, but there is someone behind you. Yeah. But of course, so the idea is that adding this kind of evolution to your system is not by default an interesting method to construct interesting ecosystems. So one of the oldest papers I found where they did this was this paper from 2008. So here they have a whole number of plankton species, and they have 50 resources. So the maximum amount of species that can live together is 50. So they choose here parameter system where you have 50 living together, 40, and so on and so on. And then they start adding this evolutionary dynamics to it. So they started adding new species and throwing out species when they go when they come below a certain threshold. And you can see that immediately this population starts to collapse. And of course, they're doing something different than I'm doing, because otherwise my story would also end here. But so they are using this Liebig's law of the minimum, where you just said that the growth rate is not like you have here the sum over all these things, but you replace the sum by the maximum. Minimum. So you're really, how fast you can grow is really limited by the resource you consume the least, or have the least access to. And if you set up it in this way, so replace the sum by a minimum statement, then this whole evolution approach does not work and the whole thing immediately collapses. At least that's what they reported in 2008. I still have this idea that maybe if I run it myself, something else happened, but the paper was well written and it's actually quite interesting to read. So I think I believe them for now. Yeah.
And does it collapse faster even than if you wouldn't add the evolution?
Yeah, because so you see, this is these are all stationary states. So they chose the parameters in such a way that you have these stationary states. So that's what this dotted line mutation begins.
Okay.
So here we have a stationary state. You start adding new species and then the thing collapses. And you see that if you start here very low, you go up a little bit.
Sure.
But it's just, that is why they say in the title evolution exacerbates the paradox of the plankton. I mean, it gets worse instead of better. Yeah.
What is the K?
Sorry?
What is the K?
K is the number of resources. There are 50 resources. And you see that the evolutionary stable value here is something around way lower than the competitive exclusion principle would give you. Yeah.
It feels a bit counterintuitive to start at the state, start adding more species, and by adding more species, more tie down to get less species, right? That's what you're saying?
Yeah, so indeed, so it is some sort of, you would hope that if you start adding more species, that something interesting happens. What you see is apparently to get to this point 50, there is a very detailed balance between all these 50 species competing for 50 resources. And the moment you start perturbing the thing, it just collapses.
You get species that are super good and outcompete all others, but
well, it depends on how they choose their invaders. I mean, if they have, I can't remember from the top of my head if they have a budget introduced here or not. Because otherwise, indeed, this could be the case. But then, of course, there could be a new species that, could also be, yeah. I can't from the top of my head.
So what else could explain it? Except for one of these perturbations is beneficial to that species and it outcompetes the rest. What else could it be?
Then I think we should, during lunch, actually go through this paper again. Yeah, I looked at this probably 4 or 5 years ago, and then, yeah.
Okay.
So the thing that we started working on already, something like, let's say, a physicist, so Joshua Dijksman, as a co-author, started working about this somewhere back in 2015, 16, and, running some simulation. At some point, I got involved when we were both still in Wageningen. And here we're looking at this just a resource consumer model. So again, we have resources and we have species. And we introduce here a budget. So we assume that, so how well species J can consume resource I is given by Sij. And so the sum over all these coefficients should be 1. Meaning that if it wants to become better in consuming resource J, it should become worse in consuming the other parameters. One of our students always explains this like, if you have an exam the next morning, you should optimize between either studying or sleeping. You can't, stay up all night, study till 4 in the morning, and then be very groggy at your exam, which is not optimal. But if you just go to bed at 10 o'clock, then you probably didn't study everything you should study because your planning wasn't very optimal. So there's some sort of you can either study or sleep, but you can't do both. And of course, it's the same idea here for species. And the interesting thing is you can prove here a mathematical theorem. That is that if this resource vector gamma, like these replenishing rates here, if they are in the cone spanned by the resource vectors Sj, so we have this whole matrix, they all have columns, all these columns span a cone in Rn, and if this gamma is contained in this cone, then all species in the simulation will coexist. And of course, this is, sorry?
Tillman, 98.
I will believe you. Yeah.
That is the generalization of Tillman's work David Tillman's work on resource competition. He is famous for it. He does it for 2 species, but he has actually checked it for different algal species and different. So experimentally, he has actually tested it.
Yeah. So I got this theorem. So I didn't do this myself, of course. I got this theorem from this paper, which is significantly later than yeah. But of course, then, but also, of course, the mathematics. There is no, in some sense, the mathematics you need to understand this is just linear algebra, and of course, these ideas of linear algebra. How can you use this to understand populations? Has been floating around the literature for ages, and of course, always in different contexts, these things surface again.
They have something more than that.
Sorry.
If you get to PIL, like editor suggestion, it cannot be just linear.
No, of course it's not. It's not just. I mean, I don't have these papers that you mentioned from the top of my head. Of course, I know the names, but I haven't read them in detail. So I assume that these things are not just a copy of these papers. But of course, so they have these figures. So of course, we have here 3 resources, and these. Because we have 3 resources and we have this constraint that your consumption rate of these 3 resources sum to 1, you can represent it in a 2-dimensional point. So we have all these values between 0 and 1. We have 3-dimensional points, you can represent them on this triangle. And this gamma here represents, so this diamond here represents the replenishing rate of the different resources. And you can see that if you have this system, these are all the strategies of all the different species. You start all here at this point, and you can see that if you run the simulation, then only this species survive and all the other species go extinct. But if I now add an extra species here, you can see that all these species coexist together. So this is what ecologists would call a keystone species. So similarly, if you have this ecosystem and I would now remove this orange species, the whole ecosystem collapses. So you're not adding, so the amount of influx in the system, like how many nutrients are you adding to the system, doesn't change. But it's just by removing this one species, this whole ecosystem immediately collapses.
Is it clear where this theorem about the cone, can you see that from this simplex?
Yeah, I mean, the cone is just, if you just draw a line around
it's just the convex hull.
The convex hull, yeah, it's just the convex hull of all these strategies. And here, this diamond is in the convex hull of all the strategies. And here it's outside. Yeah. Yeah.
Is this steady state unique?
No, it's really dependent on the initial condition.
Okay.
So you have this whole plane, this lower, yeah.
The theorem says that all the species survive, right?
Yeah. Or at least you can pack infinitely many species together.
You can pack infinitely many species together. Yes.
Yeah.
And okay.
I'm not sure if that means that all initial conditions converge to a state where none of the species went extinct. I'm not sure if that's the formulation of the theorem, but at least you can, if you do, yeah.
Yeah, but it also.
But it just means that if I just add another species to the system, as long, yeah, I mean, you can just, in this case, you can just adding more and more and more and more, yeah.
You can fill the whole convex hull.
You can fill the whole convex hull with species, yeah.
The star, it's kind of like what the gamma was in the other one, but
Yeah.
what is it like physically, how do you get it?
It's just so it's a very theoretical thing in this case. It's the replenishing rate. So you actually have to think of here more like an experimental setup. You have your whole box of liquid wherever your bacteria species are living, and I just have these different pumps of resources that are flowing into my setup. And of course, in the sense to which this makes sense in a biological context, then gamma is probably varying and of course also resources can have their own dynamics. I mean, if you think of a resource like grass for bunnies, then this is really not well represented by just a fixed inflow. That's not how grass works. Yeah.
Is there some kind of constraint on the sum over I of gamma I? Because it's also on this simplex. Or could it be outside the simplex?
Of course, to make this figure, it's projected onto the simplex, but of course it can be
Right. Okay.
3
It's
times
not
as
just-
large. No,
yeah.
it's just the direction. Yeah.
Right.
Yeah.
So if we keep the keystone species and remove some of the other species and still
Yeah. So you can remove.
find the complex.
Sorry.
If we
Yeah.
keep the keystone or
Yeah.
the orange
The keystone species. Yeah.
yeah,
So you can just delete this species without a problem. Yeah.
without a problem.
But you can't remove this one. Yeah.
You just need
And that's a unique, probably, like the keystone.
Well, of course, I could add another one here. If I add another one here and then remove the orange one, everything is fine again.
So a corollary of the theorem is that the minimum number of species that can coexist is 3. Right?
Yeah.
Because the diamond will never be the convex whole of 2 species. Basically.
No, but if I just have one species, this one species will survive.
Okay, it just says you
And-
cannot have 2.
And maybe 2 as well, probably. It is just for more. It's more than like for more than. Yeah.
But if you now look at this steady state, so what are its characteristics? I mean, there must be loads of zero eigenvalues associated with this steady state.
I think in general, it is a whole degenerate state. I mean, you have
It's very
degenerate state. I mean, you find this specifically by assuming that you have this structure of, so you have this, you're not looking at a general state space for all your species, you're looking at this one-dimensional plane, and the fact is, lower dimensional plane, and this gives you a degeneracy. Otherwise, your linear algebra would just tell you.
And it's also like, is the steady state uniquely associated with the species? Or could I have this same set of species surviving at different densities if I start out with different initial conditions?
Yes, this last one, yeah. So the specific end state here really does depend on your initial condition.
And not on the species characteristic.
No.
The color coding, right, is in the lower right panel.
Yeah.
Seems to be to correspond a little bit with the sort of vertical position in the left lower triangle, but that's not the case. That's by coincidence, yeah.
Right.
No, I think no, you're right indeed. I think there's at least some correlation. Probably should test this.
Yeah, it's really just distance from the diamond.
Yeah. So I think it is in some sense, of course.
Then it's like vertical direction.
Yeah, no, I think
Yeah.
indeed. But of course, yeah, this yellow one here is indeed the one furthest away from the diamond.
Yeah.
So I think it has some influence, but you're asking good questions, Oliver. Yeah, great. I have to think about this. And so what these people used in this paper is just the case where you sum all the resources to 1. So if you wanted to talk about mathematics, you're saying they use the L1 norm of the resource strategies.
And there is a very important assumption that you didn't discuss. That's that the growth rate is actually the same.
Yeah.
The function is the same for all the species.
Yeah, so indeed, so there's more degeneracies indeed. So it's not just a degeneracy in the sense that all this is summed to one. There is also a degeneracy in the sense that
F rates are the same,
these are the same. Yeah.
and also the alpha function is the same.
Yes. Yeah. That is alpha and beta. Yeah. So indeed, so you get so for me, of course, this is so you need a lot of degeneracies to get this exact mathematical theorem to work. The point is that so in this case, you have all these species living together. But if you would go to let's say, a real biological experiment, we can expect that our system is in some way close to such an example, in the sense that we never expect in biology that there is one species that is superior in doing all things to all the other species. So in a real biological example, there are always trade-offs. You have, nettles are very good in growing in a certain, open soil, while you have different plant species are better in growing in a different situation. So in biology, you always do have trade-offs. So even if this is not exactly the case, we expect our dynamics to maybe be in some sense close to such a non-degenerate situation. And this also means, and we will see this later in simulations, it also means that dynamics can be, if I would just, give an epsilon perturbation to all these parameters, then of course this whole theorem is destroyed. But the time scales on which we move away from the theorem, from the situation where all these species live together, these time scales that you move away on can be very long if you are close to such a situation. Which then sort of indicates that the typical timescales on which this kind of just ecological dynamics happens might be in such a long time that it also starts to interfere with evolutionary timescales.
I have a little bit of problem when we talk about the real biological systems.
I knew you would have, yeah.
Biological systems have multiple trophic levels.
Yeah, sure.
And that's not, this is all only competition.
Mm-hmm.
And large systems with many competing species and only resources. Where do I find that in biology?
Just an experiment, yeah.
It's only plankton.
Like a bucket of plankton.
Yeah, and I have heard examples of soil bacteria, living around the roots of a plant or something like. Yeah.
That's soil bacteria. That's a very
Of course, but there you also have all this whole network of the waste product of one of these bacteria is then food for the other bacteria. Yeah. So that's again also.
Gut microbiome might be. It's another issue where there are many species living together, but actually they cross feed on each other and on each other's products. So it's much more complicated than
indeed, yeah. Indeed, so
I have a hard time thinking about what type of system does actually resources and many competing.
And we will go during this talk to slightly more complex systems. And you even do 3 trophic layers on the last slide. But so the thing is that at some point we started working on this project and we used a different normalization strategy. We just didn't sum all things, but we summed the squares because this was just the guy started with, it was a physicist, and doing L2 norms is just whatever felt the most natural at the time. And at this point, it also wasn't really realized that we were making an assumption here. It was just, we have to normalize our resource strategy, so we just normalized them in L2. And only several years later, we realized that it was actually, a fundamental assumption, in the sense that whatever value for your normalization you choose really depends on the outcome of your evolutionary experiment in your computer. So it means that, so if you have this p-value smaller than 1, you will get that all the species in your system will converge to the corners of your triangle. So in this case, to these point, and this point. While if you choose a p-value larger than 1, you will converge to a so-called evolutionary stable strategy, this red point here, which you can compute using adaptive dynamics. Yeah.
So is the intuition that sort of the L1 norm promotes specialization?
No, so the L1 norm is just the border case.
Oh, sorry.
Yeah.
The L smaller than 1.
Yeah, yeah.
Sort of promotes specialization.
Yeah.
You go to any of the corners.
Mhm.
Whereas if you go to higher P,
Yeah.
you're sort of pushed towards sort of compromises and sort of hedging your bets with resources.
Yeah, you're doing some sort of a convex optimization strategy, or what is your concave optimization? Yeah,
Right.
yeah. So, and this is an example of the system where we run it for indeed for 3 resources, where you can nicely represent it in this case. And the red dot here is the stable evolutionary stable strategy. And of course, if you're a theoretical ecologist from the Netherlands, like André, then you're some sort of, grown up on this kind of ideas. But it's interesting. So we recovered this strategy in this evolutionary setting. But this means that in some sense it's also actually quite a boring experiment, because it means that in this case, evolution is very predictable. I just start my simulation, I run it, and I know where it will end up after a very long time. It will end up there. So there are no interesting cluster formation, no interesting genealogical history. It's just all species converge to this point. So in some sense, we did a very inefficient minimization algorithm that we wrote down here. Yeah. Did you have a question to one, or? Oh, okay, yeah. Yeah.
What meaning with adaptive dynamics means here?
Yeah, oh, so of course, not everyone here is a theoretical ecologist grown up in the Netherlands, so maybe I should. It's the idea that, so you take it, for this kind of, how do I explain this in 3 sentences? So you just take an instance of your system, you have a certain amount of species in your system, you write down a fixed point, and of course, this fixed point will depend on your parameters. And then you start looking for species that could invade this system. And then you do some sort of a gradient descent down all the species that could invade the system until you reach a point where your gradient descent can't go down anymore. Now you reach the point that no other species could invade the system anymore. And if you do these computations, then you will end up there. But now I'm looking at André, if I said this, summarize this correctly in.
Well, it was a good talk. So adaptive dynamics actually assumes dynamics in evolution.
Yeah.
So you are in an ecological attractor.
Yeah.
Could be a stable point, but there are also elaborations to limit cycles and chaos dynamics. And then you actually look at whether or not mutant species, so a species that is slightly different from a species that is in your system, whether such a mutant species has a positive invasion. So actually has a growth rate that is larger than 0 in that context of that ecological setting. And so it's actually a technique to consistently translate ecological interactions to an evolutionary type state.
So basically, the same method of dynamical systems from what it tell me.
Yes, but the special thing is though that it not always goes to a steady state. It's one of the you can show that actually you get evolutionary branching. So two species actually evolve into
Your ocean is stable, basically the growth rate is positive, and then you get something.
Yeah.
And just to be clear, because Then you say the different time scale, the time scale of evolution is much bigger and the time scale of the
Logical system.
Alright.
So yeah, we will come back to discussing timescales because so as I said, this is not the interesting part in the sense that evolutionary is here predictable. So I spent 45 minutes talking and we now end up at the non-interesting part. So we're going great. Yeah. So, and of course, other people have been doing similar things. And of course, one of the things is thinking like, okay, we have this forced normalization that all the rows have to sum to a certain value. Maybe we can just get rid of this. And of course, one of these examples that we found in literature is this one from 2015, where they just say, okay, we'll just write down this Capoterra type equation where each species has its own logistic term and you have all these interaction terms. And they said, okay, we'll just assume that all these interaction coefficients are, this sign is the wrong way around. Yeah, this is the wrong way around. Or I should write a plus here. So I just want to have just competition. So just competition means that all the values in A are positive. So this should be flipped. And of course, the thing is, of course, we start again introducing new species. But each time we introduce a new species, we have to some sort of decide what is the interaction between the ancestor species and the daughter species. So this is just a parameter that I have to set in my computer simulation. Of course, you can choose this to be very strongly negative if you say there is a lot of competition between the parent and daughter species, or you can set this very small if you assume that there is hardly any competition, but this is just a parameter that you can set in your system. But anyway, you have to put in a negative value there if you assume that there is a negative interaction between these two species. But the point is, what now starts happening if you start running these simulations is that, so we have all these species interacting. So if there is a certain perturbation step, so I add a new species which has, certain perturbation of the rows of A. And if these values are less negative, this means that the interaction between all the other species becomes less strong, which is advantageous for a species. Which means that for all these species, all the newly introduced species that have smaller negative values are an improvement over the already existing species. Which means that there is this very large drive in this formulation to just having a matrix only filled with zeros. It can become positive because we enforced them to be positive. Sorry, now I'm still talking about different signs. So that there is a really strong drive in getting these small values in A as small as possible. But I'm still at every perturbation step, I'm introducing this interaction coefficient. So at some point, the only interaction that I have in my matrix are the interactions between mother and daughter species, and all the other interactions will be pushed to zero by the evolution. Which means that, you do get clusters in this case, but the cluster is only dependent on your mother-daughter interactions, because after a lot of generations, all these negative interactions that you introduce will be forced to zero again. So again, this approach doesn't also really result into something that I would call interesting dynamics.
Does that look like trophic levels? Sort of different levels at which there's no competition?
But this is just, I'm not sure how you would call this. Is just all species competing against all species, which is not really a trophy.
They are.
Yeah, so all species are competing against all species.
Sorry.
Yeah. And of course, this is also a very strict assumption. So when we started working with the master students, Jorik Schaap in this project, I think something like 3-4 years ago, we were like, okay, well, just let's go of this very stringent thing that it should be negative. We just allow positive values for interaction as well. So you can get different type of interaction. You can not just competition, but also predator-prey interaction or even cooperative interactions. But again, so the same problem still holds is that you get that weaker interactions is beneficial for species because you have less problems with your neighbors. which means that over time there is this really strong drift upwards in the average of all your values in A. And if you now look at the biomass in our ecosystem here, you can see that at the moment that all the interaction coefficients in the matrix become approximately 0 on average, then the whole thing becomes unstable and explodes. So what does this mean is that, of course, in the previous paper that I mentioned here, the Stielerman version, you get stable ecosystems, but that are not very interesting. But if you remove the condition, you get very much unstable ecosystems. And of course, then you get to some sort of this problem like, okay, what would I call an interesting ecosystem in this? Yeah, go ahead.
Thing that you don't discuss here, can you go back to this equation? Is that the interaction between xi with itself has a coefficient -1.
Well, yeah, -1 over k, but yeah.
-1
Yeah.
over k.
Yeah.
Right.
Mm-hmm.
You can scale it away.
Yeah.
K.
Mm-hmm.
So this is one of the stumbling blocks in all this work, is that to get to a kind of stable, large communities, we always have to assume that the interaction within a species, among species members, is much stronger than interactions with other species.
Yes.
And so what is that interaction about within a species?
Well,
because it's,
of course, it depends on some sense in how large are the populations in your system compared to this value k.
sure.
If
But if your A go to 0, they all go to K.
yes, and then you get a very if in this case that these people considered, so you get a not very interesting system where in the limit that you only get species all happily sitting in their own value k, and that's it. Yeah.
Yeah, but my point is actually that you focus on like competition between species I and J.
Yeah.
And you don't, which then changes over time, but you don't say there is no attention for the fact that one of the fundamental assumptions is like that there is a strong competition between individuals of the species I with conspecific individuals. So what is this about? Is this a competition for resources? Or is this what is the mechanism that actually allows you to do this?
Well, I think that if you want the fairest answer is in the sense that probably these guys who wrote this paper were just some sort of trained to do this. If you write down in the same way I've been trained, if you write down an equation, you're some sort of, this is the first thing you do.
Yeah, no.
And
I understand where these people are coming from, and I understand also where you're coming from. My point is more ecological about the system, but I think that this representation has problems connecting it to the system.
Yeah, no, completely agree with you. And that is also, and of course, many of the referees also were slightly annoyed by this, because this also implies that there is some sort of, influx of resources that allows this population to be at K.
Yeah.
And if we then add a new species, which also converts to K, there is suddenly enough energy in the system to have 2 species living at K.
Yeah.
And if we add a new one, I suddenly have 3K.
Yeah.
This means that in this kind of system, there is a priori no bound on the energy in the system. It could be anywhere, but and of course, so in the simulation that we'll show later, we will see that the amount of biomass is actually quite low compared to the, n times k. If there are n species, it's quite low compared to n times k. But of course, theoretically speaking, there is nothing that limits this. And that's also why we decided to go to 3 trophic layers, where we just say, okay, we have this lowest level, which is just the resources like we modeled before. And then so you just get that this whole part becomes replaced by resource consumer dynamics. But that is just one slide saying we're doing this now and not really much results yet. But yeah.
Can I check so if you would leave it out, this minus xi over here, you would get exponential growth. or decay? Like,
Well, no, but because you get of course exponential growth, but you get you're limited by all these interactions.
right.
Yeah.
Okay, yeah.
And of course you're bounded in the sense that the higher your, if number one starts growing very fast, it means that the consumption by the other species also increases, which then should balance, might or might not balance the system, depending on, you can just kind of compute the eigenvalues of your system, and then it becomes just linear algebra problem. But so the point of this slide is just saying, okay, well, just naively removing this condition and saying I'm allowed different types of interactions, the whole thing becomes unstable. But also, if you think about this mathematically, we want to think about trophic layers. And if you just leave this thing out, what do you get? Is you get here a situation where it would be possible that, the whale is eating the fish, or, the fish is eaten by the seal, and the seal is then suddenly eating the whale instead of the whale, or whatever these things are going. So you get this very weird, there is no structure in your interaction matrix. And at some point you're like, okay, well, these things just keep exploding, so we should do something else. And of course, let's immediately go here. So, enforce a trophic layer structure on our ecosystem. So we just think we still have this thing that we will only remove on the last slide. So if your name is Andre, you can just, ignore this for now. And we just have this interaction coefficient between, we now specify prey species and predator species. And we now have this interaction between these two species. And this now gives you a interaction matrix that has a very specific block structure. Now I'm looking at, did I in this case do the signs correctly? And in this case, the signs are, well, it just depends on how I define A. I define A in such a way that these signs are correct. Yeah. So it just means, so you have all these negative interactions on the prey species, and of course in the way that, so the consumption by the predator species is then, consumption by the predator is just how much you can consume multiplied by some factor beta that is smaller than 1, meaning that there is some loss in energy going from the first trophic layer to the second trophic layer. And now we do this speciation approach. So we start with just a single predator and prey species that live in some state. By our assumption, we don't get any limit cycles, but we get a stable fixed point because of this term here. If you set k to infinity, we go back to nice oscillations, as Andre pointed out on my first slide, I think. Yeah. And of course, then we start to speciate. So we choose a species change on biomass. So the higher your biomass is, the more likely you're chosen to produce the next species. And we have these waiting times between speciation events are distributed. And we also assume that these waiting times are much longer than the typical time scales of this interaction between the predator and prey. And then, of course, every time we choose a species, we update our matrix P, and then and this in Jorik made this nice picture. So we have here this prey species that is an interaction with itself and the interaction with the predator. And for example, now I introduce a new predator species. It means that the coefficient, so this interaction coefficient here is just P11. So what becomes P12? P12 then becomes P11 plus Q, where Q is a small random perturbation. And then we just keep on going. And
you only perturb the predator?
No, predator and prey. Yeah. And of course, it's just, but if you do the thing here, for a predator species, you have to do it exactly the other way around. So you choose then something for B transpose and put it back into B. Yeah. But
Maybe I don't understand the term, but if you choose a species based on biomass, don't you then create a lot more? Suppose you have a species that's just larger as the individuals are heavier, would that mean that they get selected more often?
Yes, if my values here would actually represent some actual physical thing, and here they just represent, it's not biomass, maybe the correct term is just like the value of my vector in Rn, which is, yeah, just slightly more abstract than the actual mass of an elephant. Yeah.
Sorry.
Yeah. And so here we show a short time simulation. And what you see here is, of course, in the beginning, you converge exponentially fast to a stable state. And then at this point, a new species is introduced. And then again, you converge exponentially fast to a new stable state. And then nothing happens for a certain time. And that's why I zoomed in here. You can see that you get this oscillatory dynamics towards a new stable state. And then the system is in rest again. And then here again, you introduce a new species. Here in rest again. But you can also see that over time, the more species you keep adding and adding and adding, is that this nice separation of timescales that you have at the beginning, you lose the separation of timescales. And you get these more and more and more species interacting, and the typical timescale on which the dynamics happens suddenly becomes larger and larger and larger. At some point, the timescales on which the evolutionary dynamics and the ecological dynamics happen start to mix. And this always happens, it happens very fast. So this is a short simulation. For the most typical simulation for averages I compute, I run, I think, 10 to the power 6 or something. So this is a short simulation. But already here you see that immediately in the beginning you get this mixing of timescales. And of course you can now run the simulation for a very long time. And indeed you can see I go up to 10 to the power 6. So the picture you saw in the beginning was somewhere just around here in the corner. And you can see that you get to some sort of limiting behavior where you get typically around, let's say, 40 prey species and let's say something like 20 predator species. Of course, you can do analysis of statistics on this, and you can see that if you sum all the different species together, you get actually quite complex ecosystems. You have something typically like 80, 90 species living together in an ecosystem.
With how many do you start?
Just one predator and one prey.
Just two.
Yeah. Yeah.
Do you have this specs of keystone species in this game?
No, there is no
keystone anymore.
There is because there is also there's no keystone species and there is no normalization.
And you still you're still in the situation that the number of resources is larger than the number of species.
Well, yeah, there are no explicit.
Well, your prey species.
Yeah, of course. If you
prey species can grow on their own. So
indeed,
they have logistic growth.
Yeah.
They can grow in the absence of any predator.
Yes.
They can just all persist.
Yes.
Number of prey species is larger than the number of predator species. So you
indeed.
don't solve Hutchinson's plankton of paradox.
No, indeed. It's just what I. But also, I don't think that you can solve paradox of the plankton in just one soup, in the sense that it's a complex thing, in the sense that there are a lot of ingredients that you need to. No, but I mean, I think is that so. What for me, the interesting part is whether or not that you get this mixing of timescales. But indeed, you're right that the amount of prey species here is much larger. But also, it's something that you expect. I mean, if you just look at the statistics of if you just start counting animals somewhere in the field, you always get to some sort of 2-to-1 or 3-to-1 ratio between the number of predator and the number of prey species.
Seems to be a slow upward trend here.
Yeah. Yes. And this is also indeed the same thing I mentioned before, something that the referees really, really did not like. Yeah. But apparently in the end we're cool with, but yeah. No, but there is indeed some sort of slow trend upwards. Because yeah, there is this possibility of adding more and more biomass.
But just can you go back to the picture? No, that one. So what you meant by mixing time scale with that, you start observing the emergence of new attractors, right? But the statistic of the attractors after some time it like converts to some invariant measure, like on the slow time scale. Like here is adaptive time step, like so this is slow time scale. I mean the dynamic on the slow time scale will relapse eventually to some environment measure if you have this stochastic system. But the one on the fast time scale keep changing the attractor. This is what you mean.
Well, not numerically, I don't have any separate time scales. So this is just numerically, this is just the time scale of the system. It's just that, so I'm just running my ODE simulations on the same time scale as I'm running my evolutionary dynamics. It's just that here I'm just doing a lot of computations that are completely.
I understand it, but it's like the okay, sorry, because maybe my background physics, like in the Glasses system, you only run the simulation for one time scale, but then there is second time scale that emerge over the course of the dynamic. Because like for the like one time scale, you just observing the attractor of the system, but the attractor structure can change, which slowly emerging. Okay, we can talk about it later.
I'm not sure if I understand where you're going with it. Yeah.
Christian, is
Yeah.
your mixing of timescale not simply due to the assumption that you make about like that new species are added based on the biomass? If the biomass grows over time,
Yeah.
you show,
Mm-hmm.
you know, then the likelihood of a new species occurring is also getting larger over time.
Yeah. No, you're right. Is that the so the such of course the exponential waiting time depends.
Yeah.
But at the beginning of my simulation, I have to some sort of introduce a reference value. Like I say, okay, if my mutation rate, you know, divided by a certain biomass, and as a typical biomass, I choose quite a high value. So we are, so as a biomass value that as my reference value, I choose a typical value we have around here. So this means that in the beginning, the dynamics is indeed quite slow, but it doesn't become very. So I think that I start with, you know, the typical waiting time is, you know, every t is 1,000. That's the average of my exponential waiting time, and at the end of the simulation, it has gone down to something around t about 700.
Yeah, but
So it has.
Is that for each species separately? Because your number of species also grows. Like, you know, if every species has the same, has a similar type of waiting time, which actually decreases with the biomass of the species, then both the increasing number of species and the increasing biomass might actually explain why you get this speeding up.
No, because what we do here, we do the waiting times between speciation events, and this is between speciation events in the whole ecosystem. So this means that so I choose a waiting time, I wait for a certain amount of time, and then I choose one species to speciate. And this
waiting time between speciation events becomes shorter with increasing total biomass.
Yes. Yeah.
Okay.
But this is why I set the initial biomass to be quite high to prevent it to be, But so what I think is, in more mathematical terms, if you want to understand this slowing down, at some point, or a previous, I mean, there have been, I don't know how many iterations of this model, I computed for each speciation step, I computed the stationary state, and then the stable state, and then computed the largest eigenvalue. So of course, the largest eigenvalue is still negative, but so I computed the one most close to the imaginary axis, which sort of determines the typical timescale you expect your system to evolve on. And then you will see that these largest eigenvalues, they start, let's say, somewhere around -1, and they converge very fast, very close to 0. So this is just, if you want to understand it in that mathematical sense, is that you get this dynamics of the eigenvalues of your stationary state becoming very close to 0, independent on how you choose your exponential waiting time. Let's say, okay, why does it's just slow. This is the slide we're now ending up. Yeah.
Wow.
It's beautiful, isn't it? Yeah, that's why I put it. So of course, one of the questions that I had is whether or not how many species in this system are now just living in the system because I just keep on adding new and new and new systems. Is it possible that if I now stop my evolution, we just filled the whole system with species that are just bound to go extinct? And the answer is no, at least not typically. So this is one of the simulations. I ended here with 82 species. And then I stopped speciation and just let the system equilibrate and see whatever happens. And then in this case, only one species go extinct. So it's not that our system is completely filled with species that are bound to go extinct. Most species will survive. But you also see here, so my initial species waiting time was 1,000. So in this case, it has been reduced, I think, to something like 650, somewhere like here. But you will see indeed that the time it needs to equilibrate, something like that, is actually like 5-6 times larger than this typical time scale. And of course, the question is then, okay, but how stable is this system? If I give this a kick, what happens? So I just took this end state, gave it a kick, and you see that all species survive. So none of the species go extinct. So this is a very robust system. Of course, but this is mathematically some sort of built in because I have this very strict structure of this block structure in my matrix, and it just some sort of stabilizes the whole system. And of course, now the question is, so now we finally get to the clustering part. Because I can say, how do these genealogical trees look like? And this is for the pre-species of the previous simulation. And you can build these kind of genealogical trees. And you will see that in this case, you can really nicely define clusters just by saying, okay, well, just by looking at it. I mean, these clusters that I defined here make a lot of sense. So you get this nice separated different clusters of species.
And they're clustered with respect to data. Or what?
No, here they just clustered. Now here they clustered based on distance to ancestor.
But the distance in terms of
how long ago it was that they split.
Yeah. Okay.
This is just how long it is again that they split. So all these points is the moment that one species separated from its ancestor.
Okay.
Yeah.
Wait, where are the species that did not survive?
They are in the next slide. And of course, with this,
No, but in the tree, so the tree is only for surviving species.
Yeah.
Okay.
So indeed, this does not work always, but when it happens, it's nice that you can just say it's the next slide. Yeah. But this is the full tree for all the prey species. And you can see that here, here you have a family that looked reasonably successful at this point, but then it disappears. And so here are the 1, 2, 3, 4, 5, 6 clusters that we found at the end. But you can see that it's just nicely branching and things disappearing, and
So that's what I was wondering about this, because you have this tendency to go up in the number of species.
Yeah.
But perhaps that just says that somehow diversity is increasing, but actually the number of clusters stays stable for long. Is that something you see?
Well, that's a very difficult question, especially because this would also involve simulating significantly past the 10 to the power 6 that I did now. Actually, if you simulate to 10 to the power 6, you get cluster formation. But if you want to see something interesting happening on the dynamics of these clusters, you will need probably a whole order of magnitude extra to see what's happening on these clusters.
And that's computationally
difficult, yeah.
How long does it take to simulate these million times?
I think one of these things is 20 minutes, so that's quite doable. But that's quite fine. I mean, but the main thing is storage. You're in your computation. So at least in the way I set up my computation, I'm pre-storing something like 10,000 possible species that could happen at some point in the future. And if you want to go to 10 to the power 7, you will need to store significantly more species. And you don't want to, pre-compute a matrix of, a million by a million species. So you probably need to be. So the reason I did it like this is because you can be very lazy. I can just, specify a whole matrix, and only when a certain species becomes activated, I fill this row in my matrix. But if you want to do it efficiently, you have to then delete species that are no longer there. But it also means that you have to delete the index of the species. And then if you delete species 5, then species 6 suddenly becomes species 5 in your row. And then you have to start thinking. And that's, of course, not my favorite part. Yeah.
Sparse matrices.
Well, of course, I use sparse matrices in the sense that indeed, if a species goes extinct, I fill that row in the matrix with zeros. And that makes your computations faster, but you're still working with a matrix that is a 10,000 by 10,000. Yeah. And if you would go longer, then you have this sparse matrix of 1,000,000 by 1,000,000. That's still not.
Yeah. If that's the bottleneck, then you can do it.
Yeah. And of course, what I would do is just be lazy and then say, okay, I simulate up to all my 10,000 species are, my matrix is full. And then I just write this whole thing away, keep the existing species and start over again. And then you have dictionaries or And so I wrote a whole master project saying this is something you can do, and nobody took it. But that's especially also because you talked about this cluster formation, and so one of the questions was we have this variation between how large is the noise you introduce in each perturbation step. So you introduce a new species to your system, which is a small perturbation of an already existing species. And if you make this variation very small, so that means that the daughter species is very similar to the ancestor species, you lose this whole cluster formation. So you get this very extensive tree and you get way more species living together. So this value that I showed, that let's say we're having 80 species living together at histogram, really dependent on how large do you choose the noise in each of your speciation steps. So if you make the noise smaller, you get way more species living together. And then, of course, the interesting question is, if I now run this simulation, an order of magnitude longer, would I also start to see cluster formation here? And I think the answer is yes, probably, but it's just something I can't do with my current honky-tonky MATLAB program. But it's just,
Why would you expect it to see cluster formation? Because this result, isn't this simply due to the fact that if the variation of your daughter species is small compared to the mother species,
yes,
then the time for to go extinct or to settle to a new steady state also gets much longer.
Yes.
So and that you keep repeating, even if you simulate for 10 to the 9th time steps, because you could keep introducing species.
Yeah, but then you would assume that if I would stop speciating in this case, that a significant portion of these species would go extinct.
Yes, that's what that I would actually expect. Yeah,
I don't think that is the case. Now, the question is, did I explicitly check it? So I've checked it, of course, for the case that you just saw in the previous, but I'm not sure to what extent I did any systematical analysis of how many species go extinct for small noise values. But I don't think that would be the case, actually. But I would also be perfectly happy if the result is there are no cluster formation happening here. But I think so what my idea is that, but this is just wishful thinking to some extent, is that this noise parameter that you introduce sort of indicates a time scale on which these clustering effects happen. And therefore, if you would just go to the genealogical record and you see periods where, a lot of diversification is happening, you see a lot of different branches starting to exist, for example, after the KG extinction event. That's a time with a lot of noise, so you see a lot of clustering things happening, while not. Anyway, that was some sort of the idea. But as I said, there was no master student that wanted to do it.
But if can you go back to this graph, because this graph is very different from the ones that you showed, from the one that you showed first.
Yeah.
But that's because you only graph surviving lineages.
Yeah.
Because this one gives the suggestion that there is much more speciation going on. also in the beginning. But that's not the case.
No, they're more surviving. Yeah.
They're more surviving.
Yes.
So it would be interesting actually to include also the extinct branches, because then you can maybe see better why this actually happens, why you find this large array of prey species.
So you mean you want to see this figure, but then for the
in the gene,
Yeah.
just like we do in you do in phylogeny, that you also show extinct branches of extinct species.
Yeah, I think I should be able to make the same figure for and I should be able to include, but the thing is, if you include extinct branches, you need to really think about how to visually represent it, otherwise you get just complete chaos. Yeah. I mean, even producing this figure is just, your GPU doesn't really like this, but this is probably also just me not being very good in computing these kind of things. But anyway, I mean, also given the time and people maybe start getting hungry. So of course we can, so the way I defined clusters in this sense was just by looking at, times they diverge from their ancestors. But of course, there are also different ways you can think about it, like functional differences, like how different are the parameters of the different species living in my systems. Or you could look at the interaction strength between predator and prey. And of course, the question is, how can you now nicely visualize this? So here, for example, I have this figure where I also not just varied the interaction parameters between the species, but also allowed the growth rate of the prey species to vary. And then you can, and then I also colored these points on how related certain points are, and then you get these different branches starting to exist. But yeah, and then you can also see here that you get this constant splitting of branches, and also it looks like these two branches here are merging, but it's just that these different branches now have the same R value here, but the underlying structure, the interaction with all the existing species is actually completely different. So if you now, for example, look at let's say the growth rate, so here's the same value that was on the y-axis in the previous figure, now plotted versus the total predation rate, you can see that you can nicely separate out all these 6 clusters that we saw before. And so even though these, how do you say this? For one R region here, we have 2 different clusters that are separated by how they interact with the predator species. So you would think if we just have a higher growth rate, that these species should be better than these species because they can grow faster, but they have a completely different group of predator species that they interact with. You can also see that if you do some sort of modularity algorithm. So this is the interaction matrix color-coded. So you have the zeros between the predators, zeros between the prey, zeros between the predators, and interaction coefficients. But if I now ask a modularity algorithm in MATLAB, and I have no idea how this works, this is just a black box for me, but it says you can split your interaction, this 2x2 blocks, you can split it into a 4x4 block. Just depending on the interaction strength. And then you will see that, so you get these, this exactly overlines with the upper branch that you see here and the lower branch that you can see here. So even though these values overlapped here, the interaction strengths are just still encoded in this matrix and give you some sort of the upper branch interacts very strongly with the certain group of predators, and the lower branch interacts very strongly with a certain group of predators, but the interaction between the prey species of the lower branch is then very weak. And also, if you would look, for example, like at functional differences, like how different are certain species by just measuring the squares of the differences, and then you can apply k-means clustering to these functional differences. You can also see that this some sort of genealogical history is completely encoded in these functional differences. Like if I, for example, ask k-means to find me 2 clusters, it says, okay, it nicely separates out these 2 clusters, so the upper branch and the lower branch, and then I say, give me 3 clusters, and then it separates out these. And if you then would compare this to the genealogical history, you can see that just applying k-means clustering to these functional differences really is also completely encoded by the genealogical distance. Does that make sense?
Mhm.
Yeah. Okay, now we get to the conclusion slide. This, if you want to find interesting dynamics, so if you want to find these kind of genealogical trees with structure and interaction between groups of predators and prey, you actually need to at least enforce some structure. You can't just get away with having no structure. But under the right parameter setting, you can actually find some rich and interesting dynamics. And of course, the question is now, can we extend this in some way to make it more realistic? And of course, long time ago when I wrote this slide, I said the system can be easily extended to make it more realistic. But of course, then we got a master student who started working on this, and actually it turns out that it's not so easily extended, but of course that's science. So these are the last slides that I added this week. So you have now Loes Bijman who's working on this. And of course, we try to do now 3 trophic layers. So instead of just having some sort of predator-prey interactions, we now do the resource consumer top predator, or as we generally call it, grass bunny and foxes. But then again, here the main problem is that there are just an endless way of how your system can look like. If you just go into the literature and ask for, can you give me an ODE system that models grass bunnies and foxes? There is just a complete zoo on different interaction coefficients that you can use, different functional forms, Hill functions, and so on and so on. And therefore, if you just implement some choice and it doesn't give you interesting dynamics, and the question is, yeah, what's going on here? Did I implement it wrong? Or should I just run more simulations and see what happened? Or is it just that the whole idea was not a very good idea? And this just takes a lot of time to figure out, like, why doesn't my approach work? And of course, again, this is science. But so in the end, she produced this figure. And of course, the question is, how do we introduce a top predator to such a system? And of course, here again, thinking about timescales is very important. So for example, what we did here is, so here we have a fox living together with 2 prey species. And then we introduce a 3rd prey species. And of course, this 3rd prey species is now not hunted by the fox because it's new. The fox doesn't know what to do. But this 3rd prey species is now consuming the resources and therefore lowering the growth rate of the already 2 existing prey species, which immediately go extinct because of that, because you still have the fox hunting them, and then the fox goes extinct. And then nothing happens. So what you mean is that in the time that this new prey species is introduced, also the fox needs to start immediately hunting this 3rd species. Or at least over a certain time scale, it should realize, hey, this is interesting, before the whole system collapses. But then of course you could say, okay, well, let's say this new species is introduced. So the fox can start hunting this new species a certain amount of its budget, like we increase the budget it hunts the blue and yellow species, but it now gets a small time, short amount of its energy can spend in hunting the red species. But then this new species, it turns out to be not very successful, so it goes extinct. But then the fox is spending time hunting a ghost species, and then the whole system collapses again. So what we now, the last method to introduce is that you actually, introducing such a budget doesn't really make that much sense here. You can actually probably increase the budget. Like if there are more species, the fox can also start hunting different species. But then again, so thinking about how do you implement this is actually quite difficult. And also there are just many different options in which your whole system immediately collapses back to, most of the time, no top predators. Which then, of course, the question is, can we already learn something about this biologically? Of course, we know that ecosystems with top predators can be quite fragile. In the case, if some large shift in the ecosystem occurs, you often see that the top predators in a system go extinct, while the lower generalists more easily survive. But that's maybe a too premature conclusion to conclude from these figures. But it just says that extending these two type of systems to a tree-trophic layer and finding interesting dynamics is actually quite tricky. And that's it. Thank you.
We had a lot of questions.
Probably you can just.
Yeah.
Yeah, I have one more question. Did you study the network of interactions in the sense of like what is the average number of race species that forages on?
No. But
Because in principle, you could actually get the same result with just every predator foraging on a single prey, right?
yes, yeah. Of course, I could construct an artificial system where I have
So the question is like, do these predators actually interact in one way or the other? To what extent?
Yeah, because we have no interaction, because we have forced the interactions between the predators to be zero and between the prey species to be zero.
Yeah.
This indeed allows you for a very boring case where you get all these just infinitely, yeah.
I guess that the modularity analysis showed that that's not happening.
Yeah.
No, but you would
Yeah.
like to see to what extent, so how strong is actually the interaction between predators.
But of course, nothing would stop this. I mean, so I get these two branches in this modularity, and you could see that the modularity algorithm showed the interaction in these two branches. But of course, it would still be possible if you then let t run to infinity, that you would get all these different branches but only exist of one. Yeah, this is not something that is exclusive.
Fully modular.
Yeah, yeah. But then, of course, then again, you get back to the question of timescales. Like, yeah, maybe this is possible, but by the time this happens, and we're already at the heave death of the universe. I mean, yeah. Okay. Yeah.
Thanks.